Hello, everybody, and welcome to this month's North Central Climate Collaborative webinar, featuring Greg Klinger, an extension educator with the University of Minnesota Extension Service. Greg is an extension educator who works in the area of climate, soil fertility, nutrient management, and water quality. Without any further ado, I will go ahead and turn it over to Greg for his presentation. Thank you all for joining us today.
Great, thanks Hans, and thanks everyone for being here today. As Hans said, my name is Greg Klinger. I work for the University of Minnesota in an agricultural climate resilience role and have a long background with nutrient management, research and outreach. The climate resilience role is actually fairly new, but I just wanted to share some of my thoughts about kind of the impacts between water quality excuse me, and climate and nutrient management. And I guess also I'll just mention kind of right off the bat before I share my slides, came down with a bit of a cold last night, and in the interest of not having everyone see me up in the corner of the screen kind of dabbing up my nose and eyes, I think I'll actually turn off my video before as I share the slide presentations, and then just bring it back at the end. Okay, so I'll go ahead and get started. Excuse me. All right, so the title of my talk today is Managing Nutrients and Water in a Changing Climate. And I'm really focusing on kind of mid-century kind of thoughts on what the climate might look like, and focused on Minnesota. I kind of was, after I put this title together, I thought, it's a little bit unfair because while Minnesota is the land of 10,000 lakes, the lakes are very unevenly distributed. And I'm actually in a part of the state where there are very few of them. So it maybe is not the most appropriate title in some ways. So Minnesota it's a big state, especially north to south. And because of glaciers and climate, has a lot of variability in soil slope, soil types, soil chemistry. And that also leads to a lot of variability in cropping systems and crop management. Just as some examples, kind of this picture up to the left is from the Red River Valley, where the average elevation change is about 1 foot per mile. So essentially almost completely flat for a very long distance. In the south central part of the state, this picture, we have a lot more kind of we're at the edge of the most recent glaciation there. Much more kind of rolling topography and kind of short slopes with a lot of potholes. And then in the southeast corner of the state, which is what I'm most familiar with in terms of agriculture, we have what's known as the driftless region, which is characterized by kind of rolling plateaus of kind of mixed corn, soybeans, alfalfa, and then very steep wooded slopes down to the Mississippi River. So the average climatic conditions being experienced by each of these areas has been and is expected to continue to change. And so we're trying to think through how we can help the farming communities of the state best adapt to those changes, which is where the University of Minnesota Climate Adaptation Partnership, of which I'm a member, comes into play. MCAP, as it's known, has the vision of helping communities, landscapes, economies prepare and thrive in a changing climate. And within the partnership are a number of researchers, as well as people like me who try to connect what we know from climate research to particular areas: row crop agriculture, forestry, so on. Sorry, wrong direction. Let's start with climate. What has changed? What is expected to change in the near future? And when I look out towards the future, there are many people who are more familiar with the climate models than I am, certainly. But I want to illustrate trends for kind of mid-century, since that's still relatively close and actionable to what we're doing today. And based on what would be considered kind of a moderate emission scenario, which is called RCP 4.5. So I guess bear in mind that under a higher emission scenario, or if you're to be looking out further, like end of the century, you probably see some more stark differences. So what has changed already? Well, winter in particularly has already warmed substantially over historical averages, especially in the northern half of the state. So far, summers really haven't warmed that much in Minnesota. But in the southern part of the state, precipitation has increased very substantially over time. And I've lived in Minnesota for about 7 years now. In that time, we've broken all-time precipitation records for any individual place in the state in both 2016 and 2018. And then in 2019, the state as a whole, so average precipitation across the state, actually broke the all-time record as well. So it's been a very, very wet decade, rather compared to historical averages. Now, how is it projected to change? Again, thinking about mid-century, so this would be comparison of, excuse me, 2031 to 2050 as compares to 1981 to 2010. Probably not surprising to most people. We're expected to continue getting warmer and wetter. I have a couple maps here I wanted to point to. This is from our neighbors across the river at UW-Madison. And we're doing some statistical downscaling of climate projections. And what we're seeing here is change in annual precipitation across the state in that mid-century range and annual temperature. And excuse me, compared to that 1981 to 2010, excuse me, reference, annual temperature is expected to increase around 4 degrees during this time frame, and most of the state, minus kind of the very extreme southwest corner, is expected to have an annual change in precipitation about 5 to 10%. But these changes are not expected to be evenly spread across the year. So summer months, June, July, August, are likely warming quite a bit faster than they're actually getting wetter. Now, there's not really a strong signature in the models, I guess, for wetter summers, but kind of about the same sort of precipitation regime we have now. Spring is getting wetter. The fastest warming is occurring in winter, and then the biggest precipitation changes are occurring in winter and spring. So one other thing that is being projected for Minnesota's climate that I think is really of great relevance to agriculture, and it's a trend we already see, is a large increase in high intensity rainfall events. So what I have here are maps, again, from UW-Madison. On the left is that, compared to that reference time frame, it is the average number of days per decade with precipitation greater than 2 inches. So a pretty high rainfall, not completely out of the ordinary. And then on the right is, under that moderate emission scenario, the expected changes in frequency over a decade. So what you can kind of see on the left is, depending where you are in the state, about 4 to 14 instances of 2-inch plus rainfalls per decade. When you look at the 2031 to 2050 period, which truly is not that far away, you see an average frequency, especially in the eastern part of the state, it's all kind of averaging about 12 to 18 of these events per decade. And you see similar trends for, if you did the same thing for 1-inch rainfalls, 3, 4-inch rainfalls, that they're just getting more frequent. One other thing I really want to highlight relates to our winters. And it comes from Kenny Bloomfeld at the State Climatology Office at the Minnesota DNR. What you're seeing here in the blue bars is average annual snowfall in inches over the course of a decade. So annual, but averaged over the decade from the 1900s to the 2010s. And this is from a location in kind of west central, extreme west central Minnesota, a very small place called Milan, which has very good long-term historical records of weather and also in climate, and also is small enough to not have any sort of heat island effect. And then in the orange bars, what you see, or the orange line here, what you see is the average number of days from November through March, which roughly corresponds to our frozen ground time of year. But the average number of days per year where you have low temperatures above 32. And you can see, while the overall snowfall is increasing, that trend is less obvious than the very, very substantial increase in winter temperatures that are stay above freezing overnight. And this is really important when you think about the potential for runoff, especially from frozen soil, because when you start to see a big runoff event, usually it's under situations where air temperatures are staying above freezing overnight. So this is really it's a trend that's of quite a bit of interest or concern to me, especially because of my background in nutrient management, because it can really affect overland runoff issues, as I alluded to. And in particular, something I'm concerned about is dissolved phosphorus runoff from things like commercial fertilizers or manure applied in fall or over the winter period. Because dissolved phosphorus in particular, it is very bioavailable. So if it gets into nuisance algae, so if it gets into bodies of water with runoff, it's pretty good at fueling algal growth. A little food for thought here. In Minnesota, our soils generally, I mean, this is historically speaking, they contain much less soil moisture in the fall than they do in the spring, which means they're much better able to accommodate rainfalls or heavy precipitation events before freeze up in that fall period than in the spring. They just have much better buffering in terms of not having runoff events. And this is kind of historical averages, I would say. And that's important from if you're having less runoff, of course, you're taking less dissolved or particulate-based phosphorus with you. And so in general, historically, you could expect less risk of dissolved phosphorus runoff from commercial fertilizer or manure from fall applied versus spring applied manure or fertilizer. Now, I do want to mention that there are some major trade-offs, because if from like a nitrogen perspective, any fall applied fertilizer is much more prone to loss than spring applied fertilizer. But from purely the phosphorus perspective and the runoff perspective, there are some benefits to fall applications. And just kind of talking a little bit about phosphorus losses and phosphorus chemistry. The thing to understand about phosphorus and runoff in general is that it's of course, episodic rather than chronic event. They happen at discrete times when the conditions are right. Rainfall, high rainfall, rain on frozen ground, or just snowmelt runoff. And so the management that's occurring kind of around these runoff events is pretty important in terms of being able to control some of those losses. And here's why, really. When phosphorus, whether it's in manure or commercial fertilizer, has even just a few days to interact with unfrozen soil, a significant amount of anything, and this is for surface applied phosphorus fertilizers, for many reasons. I should have an aside here to say that for many reasons, sometimes fertilizers applied in the fall don't get incorporated, whether that's because of the particular, because of equipment or particular management regime people have, or because purely just because the ground freezes up and after the application happens and it's unable to be incorporated. But that's not an uncommon event. But for these surface applied commercial or manure sources, the phosphorus in it, if it has a little bit of time to interact with the soil, can be bound up pretty effectively. So we just have the soil chemistry we have in our region is pretty good at binding phosphorus to it. So there's actually some research out of Iowa State that shows that the amount of phosphorus applied on the soil surface, so the overall amount, doesn't actually impact phosphorus concentrations in runoff if the runoff event occurs more than 2 days after the application. In other words, you really just need 2 days of no rain, no snow melt, those sorts of things. And as long as the soil is somewhat, that surface soil is unfrozen, that interaction can occur. And you've mitigated a lot of that loss, which of course requires both good forecast models for the short term, future predicting, but also this becomes something that's logistically harder if your soil is coming through the fall with higher moisture content and late fall is getting wetter, as it appears to be. Oops. Sorry, the slides are a little bit delayed on my end. So just another comment I want to make about phosphorus, which is that we generally see with dissolved phosphorus, the harsher the winters, the more significant the proportion of phosphorus on an annual basis that happens during snowmelt events. So as you get farther north in the Midwest and farther north in Minnesota, you see more snowmelt derived phosphorus runoff, and it's usually dissolved. And just because most of the snowmelt doesn't get a chance to sink into the ground in environments where the soil freezes hard. I've also seen, I'll just kind of mention this because I've seen a lot about this recently. Dissolved phosphorus from vegetation or crop residues. So like a cover crop, it can be a source of dissolved phosphorus that can get into water bodies, but it tends to require some pretty intensive freezing to release much phosphorus from plant tissues. So keeping in mind that snowpack's a really good insulator against harsh winter conditions. If you take a climate like northeastern Minnesota, there's enough snowfall during the winter that you typically develop a pretty thick snowpack. Even when the air temperature drops to 40 below, vegetation under the snow is going to experience much milder conditions than that air temperature. And you wouldn't expect to see a whole lot of kind of release of phosphorus from that vegetation. But if you get to someplace like northwestern Minnesota that's drier, has less consistent snowpack, and cold winters, there, without the consistent insulating benefit of of a snow layer, any sort of vegetation can get frozen much more harshly and release more dissolved phosphorus. And because the frost layer is going to get thicker during the winter in that sort of climate, it also means it takes longer to thaw in the spring, and you get more snowmelt runoff as a proportion. That's a larger issue of the kind of overall phosphorus loss budget. So all that is to say, to the extent that climate change impacts not only winter temperatures, but also precipitation and snow cover, it also has significant impacts on dissolved phosphorus losses to bodies of water. So one comment on just kind of general climate resilience and dissolved phosphorus runoff. While the context of a changing climate might mean more or less phosphorus runoff overall, there's one thing that anyone can do that is as valuable in today's climate as it is in future climate conditions, and that's just to keep phosphorus levels in surface soil from getting too high. This here is data from Discovery Farms Minnesota and Discovery Farms Wisconsin. And what it's looking at is, with the dark circles and the dark line here, that is telling you what was the average dissolved phosphorus concentration in runoff events from a specific location in a specific year, as it relates to the soil test value, but critically soil test value for phosphorus only in the top 1 inch of the soil. So, which is in stark contrast, excuse me, to the kind of typical 6-inch soil samples we take. And then the lighter one, which I won't really talk about as much, is the squares and the line here, would be tile concentrations of phosphorus as it relates to soil tests. So I won't really belabor the specific numbers, but the important thing is that this relationship is pretty good. As your soil test in the very surface bit of the soil goes up, so does dissolved phosphorus concentration in any runoff. And because pulling phosphorus soil test numbers down is a very slow, kind of laborious process, the focus really should be on keeping soil test numbers from going up too high. So this is also a value in keeping phosphorus from frozen vegetation from running off with snowmelt or runoff events. Because when you think about the big winter snowmelt events, here's what I usually see. It takes a couple of days to get started. So you might have one day where it gets above freezing during the day. The snow kind of softens, some water melts down to the soil surface. It's probably encountering vegetation, pulling a little dissolved phosphorus out of it, and then maybe thawing the very, very kind of like top skin of the soil as it hits there. But it gets below freezing overnight usually, and so that kind of runoff doesn't really take off. It just kind of allows some water to trickle down. And it might take a day or two before it actually starts to have water moving off the field. And so what often happens, if the soil test isn't too high, any of that dissolved phosphorus that's coming out of the vegetation with the snowmelt water, it can interact with that soil, and there's still some binding capacity of the soil to take some of that out of the water. And so you don't necessarily see much runoff. But as that soil test value gets pretty high, you have less ability to bind anything that's, interacting with the soil at the surface. So again, getting soil test values to not keeping them from getting too high is a critical kind of actionable item that we can do to build resilience, not just in future climates, but today as well. So I also want to talk a little bit about soil water in a changing climate. And one of the interesting things about Minnesota is because where we're located, we're very close to that kind of humid to dry transition. And in some ways, I think you could actually say we're part of that transition. Maybe those in the Dakotas would disagree, but we'll see. So this map on the right is of the state of Minnesota, and what it's looking at is where precipitation exceeds the water demand of the soil from evaporation and transpiration by plants. And so that's in the green and blue areas and purple areas on the right. And then it's also showing areas of the state where the evapotranspiration exceeds precipitation, which are yellows, oranges, reds, browns on the left. So this transition is really important because it determines generally the overall flow or direction of water flow in the soil. Where precipitation exceeds evapotranspiration, the general flow of water is going to be downwards. Where evapotranspiration exceeds precipitation, while parts of the year you might have more downward flow, there's also a significant amount of upward flow of water from subsurface to surface. And this affects the soils that develop. You get more acidic soils in the east, more basic calcium-rich soils in the west of the state. It also affects things like nitrogen management, because where water movement is predominantly downward, major nitrogen losses are more likely to be also downward through the soil. Whereas if water movement is also occurring to a large extent upwards, then there's a lot of potential for nitrogen loss from soil surface. And then it also affects things like irrigation or tile drainage, which I'll touch on here in a minute. So I found this to be a pretty interesting study, and there are a few that have been out related to this, and basically relating groundwater, talking about essentially the ability of shallow groundwater to buffer corn yields. So we know that it's not just the precipitation that falls before or during the growing season that helps produce yield in our crops. Excuse me. It's also the rise of water, up from the groundwater table that can help us maintain high yields, particularly during dry seasons. So in this map on the left, in the kind of circled area, generally speaking, soils in that part of the state have a fairly shallow groundwater table. And there's been research that shows with the kind of shallow groundwater, it does help buffer yields, particularly in dry years, where having access to that groundwater flow upwards, this helps keep yields from taking as much of a hit. But it's also a benefit in kind of average weather years, and a slight negative to yields in wet years. And all of that varies also a little bit depending on kind of the soil type you have. Heavier soils are a little more vulnerable to yield loss being too wet. The coarser soils are a little more vulnerable to yield loss being too dry. So the point is that the influence of annual or even longer trends in precipitation and just the general water budget will influence crop yields. So a longer cycle of very wet that kind of raises the water table may have negative impacts in those areas that are a little more sensitive to yield loss because of being too wet. A longer cycle of very dry might have some more negative impacts for areas of the region that are more vulnerable to the water table moving deeper. So there's a lot of interesting research there. So I do want to talk a little bit about irrigation. As you can see in the Google Earth map that I've been using here on the right, and I circled this in yellow, we do have some areas with pretty extensive irrigation in the state. And so the question arises about how might climate change impact irrigated agriculture? So getting back to those projections of climate changes in the kind of mid-century timeframe relative to the 80s to 2010, reference period. The big thing I want to talk about would be summer temperatures and precipitation. And as I mentioned before, the general trend that is likely to be experienced is significantly warmer, 3 to 4 degrees warmer during the summer on average. So increased evapotranspirative demand, if you keep all other things equal, increased demand for water by crops, but with no increased average precipitation. And so what that suggests to me is that during this time period, which is also the time period where the vast majority of the irrigation on corn, potatoes, and so on is occurring, that this is also going to lead to, at least on a per acre basis, more inches of irrigation water needed to produce a good crop than today's climatic conditions. So the other water management tool we see frequently, and this is particularly in southern Minnesota, south central Minnesota, where water tables are shallow and the soils are fairly high in clay, is subsurface tile drainage. Again, tile drainage is based on essentially lowering the water table across the field in a pretty systematic way. And that's also based on kind of average climatic conditions, what that design of that system should be. And so significant changes in precipitation patterns may make, excuse me, some of those designs less effective over time. So a question I'm curious about is, will the most kind of economic drain spacing and other design parameters, will they change as rainfall, and particularly in spring, where we expect to see pretty significant increases? As that rainfall pattern changes and rainfall intensity changes, will that lead to changes in the kind of tile drainage that's most adapted to an area? And so far, the answer does appear to be yes. There is some research from Michigan State University that compared optimum drain spacing under the weather conditions of 1990 to 2019 across the Midwest, compared to 1941 to 1990. And they found that the optimum drain spacing was roughly a meter closer together, even a little more, in that more recent time period compared to that historical time period, which just means more feet of drain pipe being installed per acre at more initial cost, potentially means more tile flow through the system as well. So one other thing I do want to think about is talk about here is just how changes in climate could affect changes in the timing of tile flow. This is some research shared with me by Matt Helmers at Iowa State University as part of the big kind of transforming drainage research that was done. It's been done across the Midwest. And it's looking at the amount and timing of both tile flow, which is this overall tile flow, which is the top part, and then nitrogen through tile, which I'm not going to focus on as much, but is another aspect of this. And it split this out by what kind of climate zone, so USDA hardiness zone, that tiled field was in. So you can see on the map to the left all the different site locations: southern Minnesota, Iowa, northern Missouri, Indiana, Ohio, and then the colors are the different climate zones. So if you look at the 4B climate zone, what you see is that almost all the tile flow is happening in spring, which is pretty typical in our part of the country. The ground's frozen in the winter. There are specific conditions that can lead to some tile flow during the winter, but by and large, it's pretty unsubstantial on a total amount. But as you go farther south, get to warmer zones, the proportion of tile flow that's happening in winter in particular goes up, while the proportion in spring goes down. And so I think what's important about that is, our future in Minnesota might not look exactly like, central or southern Iowa or northern Missouri, but they do teach us something about what we might expect in terms of tile flow patterns. And I think it is reasonable to expect that we will see a significant shift in the timing of tile flow over time, and also the nutrient losses associated with that tile. It's also probably reasonable to expect that shift in timing could also impact how nutrients carried in that tile water, like nitrogen and phosphorus, could impact bodies of water like the Gulf of Mexico, or more local bodies of water as well. So I want to focus the rest of my time here on nitrogen. It's the area I have most expertise in, and there's a great deal of interaction between nitrogen management and cropping systems and climate. So I'm just going to start off with a kind of some broad brush observations. They're not going to hold true in all situations by any means, but these all relate back to this map I showed earlier of evapotranspiration relative to precipitation. So the drier part of Western Minnesota, where you might have a little more upward flow of water in general, and then the wetter eastern part where you have more downward flow of water over the course of the year. A couple of things that kind of relate to this map. First, as the climate gets drier, the soil typically holds less organic matter and less organic nitrogen. And so you potentially have less non-fertilizer sources of nitrogen to a crop. Now, at the same time, a drier climate also generally means less nitrogen loss, particularly by leaching down to the water table, and potentially less loss to the air by what we call denitrification, which happens when soils are kind of saturated or kind of ponded for significant periods of time. So the caveat here, though, is that even in these drier soils, where the general flow of water is frequently up towards the soil surface, there can still be plenty of times of year where you have saturated soils that are ponded or a lot of water movement down through the soil. And that has historically been most often in the spring. So if springs continue to get wetter across the state, these types of losses could become more pronounced. So I just wanted to share something about soil organic matter and nitrogen supply. This is a map from a publication a long time ago, actually, that shows organic matter levels in topsoil. And again, I don't want to belabor the specifics, but the really important thing here is very high organic matter levels in much of southern Minnesota, northern Iowa, as well as a few other regions, but that being the big one for kind of our cropping systems. And I think it's worthwhile to think back to, well, what was this landscape like before we converted things to agriculture? It was a cold, wet, poorly drained, kind of marshy grasslands for the most part in this region. Cold and wet enough that the rate of decomposition of organic materials, so whatever was being accumulated by biomass during the short growing season, that was pretty slow. And so they tended to accumulate a great deal of organic matter, which also does include a lot of nitrogen. And so as we converted them to agriculture, we warmed them up, we dried them out, and we benefited from the release of the nitrogen and other nutrients that have been locked away in that organic matter. And you can really see this when you start to look at how much nitrogen is being supplied to our crops from the soil rather than fertilizer. And when you look at Minnesota as a whole, it's very substantial. It is in kind of corn soybean fields, across the state, average might be 60 to 70% of the fertilizer or of the nitrogen, being provided to an individual crop in a given year is coming from soil rather than from that year's fertilizer. So, it's very significant. And I do want to talk a little bit about one other aspect of this that's relevant to climate, which is just how nitrogen supply varies across the growing season for a crop like corn. So what we generally see in studies in the Midwest is, again, since we have rich amount of organic matter, is that early in the growing season, especially in the kind of early to mid reproductive or vegetative states, the vast majority of the nitrogen a corn crop's taking up for its own growth is going to come from fertilizer, that year's fertilizer supply. But as you get towards the reproductive stages and through those reproductive stages, it actually flips, and the vast majority of the nitrogen being supplied or being taken up by the crop is actually from soil organic matter. And the reason for that, of course, is just that organic matter decomposition happens slowly when the soil is cool, like early spring, mid-spring, but then increasingly fast as the soils warm up, like in midsummer. But the other thing to mention is that as soils get really dry, that mineralization, that release of nitrogen from organic matter drops almost to nothing. And this is actually an issue that is of quite a bit of concern to me, because if our springs are getting wetter, we'll likely lose more nitrogen fertilizer on average from our soils. because fertilizers is pretty vulnerable to loss, especially when it's wet during May and June. But if our summers are also drier, because precipitation is not increasing, but temperatures are increasing, so the demand for water by the crop is increasing, we potentially get, on average, less nitrogen from organic matter for our crops later in the season. So it's kind of getting us both ways, in the sense of more nitrogen loss early in the season from fertilizer when that's the predominant supply to the crop, and less nitrogen supply if we have these kind of flash droughts in the summer more often. And there is definitely data out there that suggests that the worst nitrogen efficiency and yields in much of our region happen under conditions of very wet springs, followed by dry summers. And the best conditions for both yield and nitrogen efficiency tend to be sort of slightly dry to average spring precipitation, followed by pretty wet summers. So as a little bit about fall urea in our area, as a colleague of mine really likes to say, nitrogen management is risk management. Everything about how you apply nitrogen fertilizers depends on climate conditions that you face. And since you can't predict those conditions very well before the growing season, beyond just thinking about averages, you're always kind of hedging your bets with your management. So an example of this is just the use of fall urea in the western part of the state. Again, that part of the state where historically precipitation is exceeded by evapotranspiration. Typically by fall, soils in that part of the state, especially like the southwest corner, get fairly dry. And so for a long time, the application of fall urea, which is compared to something like anhydrous ammonia, like I have a picture of here, is this more loss prone the farther away it is from actual crop uptake, because it's soluble in water. But that fall urea for a long time in the southwest part of the state was considered, it was an okay thing to do. Maybe not ideal, but okay. Because, and the thing to consider with urea too is that anhydrous ammonia has some safety issues, and in terms of both storage and application, that fall urea does not, and just logistical issues in general. So as colleagues were looking at this more recently in this region, well, we've had some pretty wet years, and that kind of dried out fall soil is just not as often the case. And getting back to an earlier slide, more kind of freeze thaw, warm up events during this or during the winter as well. And what they were seeing is that fall urea is actually in this southwest corner of the state becoming much less efficient than anhydrous ammonia as a nitrogen source, in terms of both pretty significant yield loss when you're applying at the same rates, as well as probably some more significant water quality impacts. So one thing that we'll probably see as climatic conditions change is just a shift in what are the most appropriate fertilizer sources and fertilizer timings. And one thing I do want to talk about there real quick, and then I'll kind of wrap up here, is the use of things like slow release fertilizers, inhibitors, nitrogen sources that are slightly different than our traditional ones, what we call enhanced efficiency fertilizers, as both a way to adapt to kind of more erratic climatic conditions, more extreme rainfalls, but also as a way to mitigate or kind of lessen greenhouse gas emissions. When you think about the impact of nitrogen fertilizers on climate, there's kind of two main ways they do impact the climate. One is just fertilizer. To make nitrogen fertilizers, you are breaking apart nitrogen molecules that are in the air and converting them to ammonia, and it's a extremely energy intensive process to do that. Then the other aspect is that when you have soils that are pretty high in nitrogen, so as fertilized soils will tend to be, under the right conditions, they can release a significant, if they get very wet at different times during the growing season, they can release fairly significant amounts of nitrous oxide, which is a pretty potent greenhouse gas. So you have a direct impact and then a kind of indirect impact just by the energy use. So there's efforts to lower the kind of energy footprint of nitrogen fertilizers in general by people are starting to build what they call green ammonia plants, which is just ammonia synthesis facilities that are being powered by renewable energy. And then the other hand, there's a lot of effort to try and reduce these nitrous oxide emissions from soils by either kind of fine tuning nitrogen fertilizer rates or lowering those rates, depending, or by using these enhanced efficiency fertilizers. So these enhanced efficiency fertilizers and inhibitors, I'm kind of lumping together a few different products. You have things like what you see on the left here is a product that is polymer coated urea. So basically it's a urea fertilizer that is coated in a substance that only allows for sort of slow water movement back across the surface. And so water comes in from the soil, it pulls out some urea, pulls it back out into the soil. And over time, that fertilizer is being released, but much more slowly than a typical nitrogen fertilizer. So that's a slow release fertilizer. And then on the right here is an application of urea with instinct, or with a nitropyrin inhibitor, which basically is a product that slows down the conversion of fertilizer nitrogen into forms that are more likely to be lost from the soil, including as nitrous oxide. What's important to recognize about these different types of products is they all add cost to fertilizer, and they don't always have yield benefits. So they're not always going to be cost effective for farmers to use. And in general, while the specifics are different for different types of products, they help maintain yields the most, excuse me, over kind of a traditional fertilizer source when conditions in the spring and the early summer are bad, so like really wet in particular, or just on more generally loss-prone soils. So the economic advantage or disadvantages using these products for the farmer is really going to hinge on whether and how much climatic conditions shift on average. They also have an upside to society, as I mentioned. Part of the goal is to get less nitrous oxide emissions with these. And there's a lot of research that started to look at that. Different studies will suggest different things, but potentially there's some recent meta-analyses that have come out that would say like a polymer or a nitrogen fertilizer with instinct or a nitropyrin inhibitor rather might reduce nitrous oxide emissions by about 50% when you compare it to like a traditional fertilizer applied at the same rate. Probably a little lower of a reduction when you talk about a polymer coated urea product, but still maybe 30%. So potentially, I mean, not every study shows that, but potentially it's pretty significant. So I think I'll just leave with this, which is there are a lot of aspects of climate change and agricultural production that obviously I couldn't touch on or didn't. But as somewhat of just a closing thought here, agriculture is and has always involved lots of adaptive management and problem solving, tackling equipment failures, unexpected pests, diseases, unexpected weather being a big one. And I think the challenge with what we kind of quote unquote call climate resilient agriculture is going to be just reimagining management strategies that work well today in the context of future conditions. So, what diseases or weeds will become more prevalent? Will different nutrient management practices become more effective or less effective? Will different types of crop hybrids be better suited to specific areas? And, some of these questions, I think can still, with row crop agriculture, remain in that realm of kind of annual decision-making, kind of thinking year to year. But I would suggest that especially as we talk about things like erosion control structures, tile drainage, deciding whether to invest in irrigation, things that might have long payback periods and also 10, 20, 30-year lifespans, it is really worth thinking ahead about how those might fit into future conditions. So with that, I think I will go ahead and wrap up here and take any questions people might have.
All right, Greg, first question, and then I'll open the poll for everybody to fill out. One individual was wondering where they could find the climate prediction figures that you were using in your slide deck.
Yeah, I know I will have to get back to you on that. We have that as an internal set, but I know it's also externally facing somewhere on our website. But this is where being only kind of 2 months into a role starts to make it harder, as I'm not as familiar with everything is. But I can is like maybe I should ask, is there a way for me to kind of touch base after the webinar, or because I can find it pretty quickly?
Certainly,
Is that
yes.
not-
So we will let everyone know when the recording is posted, and we can
Okay.
certainly include some information at that time.
Okay, I can do that because that is out there. I'll also mention that for Minnesota specifically, so that data was statistically downscaled from global models by kind of using the last round of climate models by UW-Madison. There is a current effort at the University of Minnesota to do what's called to do a dynamical downscaling of global models, kind of with the most current climate models that are available. And I doubt that will change things too much, but it's a little bit different approach that's kind of ongoing. So we'll also have our more specific kind of climate information that's actually on a 3 mile by 3 mile grid for Minnesota within the relative near future.
Excellent. Okay, we've got a direct message question. Have you done research concerning ag nutrients and rivers as drinking water sources in terms of climate change and downstream communities?
Yeah, more with groundwater, I'd say, a little bit with surface waters. So we have pretty significant nitrate contamination, in particular, in a lot of areas of like the driftless, what I call the driftless region of Minnesota. I would imagine as well Northeast Iowa and Wisconsin, but don't hold me to that because I haven't seen the data. But which has to do a lot with just the kind of geology that we have in the region that's just pretty vulnerable to, again, downward flow of water through the soil, taking nitrate with it. So with that being said, there's regarding climate specifically, the biggest factor that is going to probably influence kind of the overall nitrogen load that's, let's say, going down to the Gulf of Mexico is just how much water is flowing through the ground and into rivers and just out the Gulf. Because that is really, we see like for the last 4 or 5 years, we've been in a really wet phase. And the overall amount of nitrogen flowing down the river, because the water flow is so high, has been quite a bit. At the same time, concentrations in the river water tends to be a little lower under that time, that kind of time period, because it's essentially like a dilution factor. So you have more water flowing. The overall nitrogen being lost is much higher, but it's also more dilute. So concentrations are lower. And then kind of on the flip side, if you come off of a drought year or two, you tend to see a lot higher nitrogen concentrations in water, but the overall load of, the amount of water flowing is not as much. So that, there's a huge, aside from kind of the cropping system things, there's nothing that's probably more important than weather and climate in terms of how much nitrogen is like leaching through the ground or ending up in bodies of water.
Thanks. Last call for the poll, which should be open right now for you to fill out. I'll close it at the end of this next question. Charles asks, can you make a map of where nitrogen inhibitors might be most likely to be useful around the state?
Yeah, so yes. And you'd probably do it based off of soil series, or, like soil type. So where any sort of product that's like an enhanced efficiency fertilizer is most effective are in soils that are more loss prone. And by that, I mean, so like very sandy soils tend to lose a lot of water downward through the soil to groundwater, or very heavy soils, very clay rich soils that tend to pond water, and they actually tend to lose a substantial amount of nitrogen to the air. So those are the kind of environments where they tend to be most effective. Some types of things, at least in Minnesota, are probably on average a little more effective in different areas. I would say that, and I didn't talk about split applying nitrogen in our kind of more irrigated systems and our sandier soils. Actually splitting nitrogen applications into 2, 3, 4 applications over the growing season is more effective than any product in terms of yield and reducing the impact to the environment. But then things like your polymer coated kind of slow release fertilizers also tend to be pretty effective. And then I would, generally speaking, probably put the inhibitors a little bit behind that. But as I mentioned before, from a nitrous oxide emission perspective, the inhibitors tend to be a little better, is kind of what the research so far seems to be showing.
Okay. Now, Aaron Wilson has put in the chat a rather long question, and he happens to be co-host also on the leadership team of the North Central Climate Collaborative. So I'd ask if he wanted to ask that himself, because he has the ability to unmute.
Sure. Thanks, Hans. Thanks, Greg, for a great presentation. So there is a pretty strong evidence showing that we're entering this phase where we're seeing increasing number of rapid transitions between wet to dry, especially, or dry to wet or wet to dry. And I'm wondering if you can speak to maybe the potential or additional challenges that this might pose on nutrients across the region. We know that it's happening strongly across the southern Midwest, but projections show this expanding even across, Minnesota and Wisconsin in the future. And maybe it's too early of a question, but I just thought maybe if you can think about if there's anything that we should be mindful about these rapid transitions between hydrological states.
Yeah, I mean, I guess the big thing is it's just going to make everything more challenging. Especially, and again, I'm coming back to nitrogen because that's where I've spent the most time. But it really is kind of managing risk. So all of these practices I'm talking about, your slow release fertilizer in kind of wet conditions is going to probably work better than just a traditional urea source. But it's also, you could go into the season and use that or a mix of that with regular urea to kind of mitigate some of that risk and then end up with a fairly dry spring. And because that slow release fertilizer requires water to kind of release the fertilizer from within the polymer, you can actually have situations where that becomes then a problem for yield. It is actually hurting yield. I've never personally seen that in research in our area, but it is certainly possible. And the same is true with things like split applying nitrogen, where, let's say you were to apply half your nitrogen at planting, and you decide to wait until corn is knee high or a little higher, and then put the rest on. But let's say at the same time that, like, the 1st of June, it really dries up, and all of a sudden the soil starts to get pretty dry. So you go out, you put your split application on, a week later, it's been dry, it continues to be dry. Well, nitrogen needs water. The main way plants are getting nitrogen into their roots is by transpiring water, and that pulls water into the roots, it pulls nitrogen with it. So even something like that, you can end up having things that are designed to mitigate risk under the right circumstances can actually create risk of yield loss. On the average, that's less, but it is still there. And so I think the challenge with these kind of erratic cycles is going to be just harder to decide what to do, and kind of how to manage things ahead of time. And I do think if we had really, really good, like 1 month, 2 month forecasts, that would help a lot. But it just, all this stuff, nitrogen loss, phosphorus loss from runoff, all these things are they happen in short periods of time, sometimes just a few days. And so it is hard to kind of manage kind of on the average climate conditions for that.
Thank you. Only 1 or 2 months forecast. I mean, that's not asking much, right?
Yeah, I'm a little greedy, I suppose.
Okay, well, we've got a comment in the chat. I'm going to go ahead and read while people are considering if they might have any final questions. Justin says he recalls Giles Randall's key message that a prolonged dry period going into a wet period results in big spikes in nitrogen leaching loss. He's seen it in tile water and soil water in southeast Minnesota, for example, during a really wet 2013 spring coming out of a long, dry, late summer and fall of 2012. Just a comment on this question point about transitions. And being from the state of Indiana, I certainly understand that the longer you talk about agriculture and climate, the more likely the year 2012 is going to come up in conversation. So appreciate us getting to that point. I don't see anything else in the chat. So any closing comments, Greg, before we call it a day?
No, I mean, thanks again for having me. I'm glad we got to have, discuss this and kind of just talk about the impacts of climate, nutrients and water and kind of where that might go. And yeah, just in general, that as Justin said, that 2012 into 2013 was pretty bad. And I think many people might also remember Des Moines Waterworks lawsuit. Well, that came after 2013 when they had a very, very high nitrate concentration that required a lot of treatment. And so, it was a function of many things, but one of those things was coming off of a dry year into a very wet spring.
All right. Thanks, Greg, for an excellent presentation.